All right, good morning, everybody. We start the final topic for this module this morning. I have sent you all a message on Schoology regarding both assessment 3 and how we will proceed with this particular topic. Now, based on the printed notes that you have, most of what we'll go through this morning, most of it is already written out for you. So it's just a matter of you following and highlighting those areas that you wish to get some clarity on. All right. So we just go through, and please feel free to stop me. But as I said, most of the information is already available. All right. So let us get started. You would see in the notes, I refer to it as non-sinusoidal waveforms. And here I'm talking about complex waves, one and the same. All right. All right, so let's get started. So we have here, well, this is not exactly a square wave. What we have is really a rectangular wave. Each pulse, as you see, the height and width are different, but for the purposes of what we're discussing, let's just take it for a square wave. All right, so a square wave, what we're saying is that, sorry, we're saying is that we would have had this, for the square wave. So each of the areas above and below the axis would be equal. So in drawing the square wave in your notes, just ensure that the sizes of the pulses are the same. All right. So we have a square wave here. And from our square wave, we just denote a couple of things. For example, the periodic time, yes, that's a time taken to complete one cycle. So we start here, we go to minimum, and then, all right. So we start, all right. Here. So the time here, the time taken here would be our periodic time. Right. If we want to start at this point, then it would be here. Right, so there. Again, that would be our periodic time. So as we show here, the periodic time would be, right, so the time taken for one complete oscillation, all right, or one complete cycle. All right, do we have this?
Yes, sir.
Okay. So that's our square wave. We also note the amplitude, which is the maximum displacement from the time axis. So our amplitude for this waveform, this will be our time axis, maximum displacement. So that's your amplitude. Yep. In this case, it will be the same here. Right. So we note amplitude, we note periodic time. And if I just select an arbitrary time, if I just select the time corresponding to this point, yes, if I set it, right? So That's what we would call, or instantaneous time. So that's a time at a point, at an instant. All right. So the time at any point on your waveform, so that the instantaneous time. Okay. And for your triangular wave, all right. So in this instance, again, if we use the same principle, it is start to finish, or back to where we originally started. So if I start at this point, I would have gone down, and where I'm gonna go down again, that's where the wave ends. So the periodic time would be here. Okay. If I consider the point at which I'm going to increase, if I started at this point, let me use a different color. If I started at this point, yes, then I would have gone up, down, or where I'm going to start going up again, that would be my periodic time. So that's T. So let's just discuss a couple of things about complex waves. Obviously, these do not look like the regular waveforms that we would have considered with AC circuits. And I want you to just keep in mind that what we're going to be doing with complex waveforms is just a repeated application of what we did with in AC circuits. Okay, nothing fancy. So a couple of things, a couple of definitions that we want to treat with. The waveforms that we just showed are repetitive. All right. If you note here, we have the same period. So in other words, the time taken to complete a waveform, regardless of where we start from, the time taken to complete the wave is the same. Yes. And we see that the waveforms repeat themselves. So although I'm starting from, I'm going to start from here. Even though I have the 0 here, I'm going to start from here. So we have here one waveform. And if we were to repeat that, if we take it from here, right? So we have the same waveform being repeated. And the same was true for the square wave. So in other words, they are repetitive, and we use the term periodic to define that. Fact that they are periodic means that they are made up of identical cycles, and these are repeated. Yes? I know a lot of this is nothing new. This is something that you definitely would have done in physics. Yeah, I'm sure, you know, regardless of how long ago I did the physics, the syllabus hasn't changed that much. But nonetheless, we still have to deal with these basic principles. All right. Mathematically, the fact that they are repeated, we can represent that using a mathematical expression. And that expression would be that it is periodic if and only if the function f of t is equal to f of t plus t. In other words, if I shift the function by a period big T, it will remain the same. That's all this mathematical expression means. All right. So if I shift the function by the period t, it will remain the same. Or in other words, the waveform at a point, if I shift it, it will be the same waveform. So in other words, it's periodic. It's being repeated. Yep. And as we have established T already, it's the interval between the successive repetitions. And we have already established that that is the period of the wave. So we want to just, you know, complete a little activity. But before we do that, if we call one periodic, then, you know, what happens if the waves are not repeated? In those circumstances, we say that the waveform is aperiodic or non-repetitive. So in this instance, we start at the zero axis and, you know, let's say it cuts off here. All right. Let's say that is the waveform. Obviously, it is not repeated here, and definitely it's not repeated here. So there are different waveforms going along. And in circumstances like this, there are indeed methods to do the analysis. All right. But of course, for our purposes, we're not going to get into that. I submit to you that you have already been looking at periodic waveforms. You may not have called it periodic waveforms, but I guarantee you that before the class is out, you'll have at least one aha moment in realizing that this is something that you have already applied or considered. All right. So in terms of a simple activity, what we want to do is to add these four waveforms. So we have the four waveforms here. 100 sine omega t. That should be omega, not W. But anyway, 40 sine 3 omega t, and 20 sine 5 omega t, and 5 sine 7 omega t. Now the omega here is constant. What that is, that represents our angular speed, angular velocity, well, angular speed. So the waveform, which is 3 omega, or it just means that it's going 3 times as fast. Yes. So in other words, for omega t, yes, depending on the periodic time for this waveform, 3 omega t just means that it would have completed 3 waves within that same time. Yes. So if the periodic time for omega t is big T, then the periodic time for 3 omega t would be t over 3. Yes. Similarly, 5 omega t, yes, it just means that the periodic time would be t over 5. Since we are dealing with the same, omegas. Everybody comfortable with that? So let us then add these waveforms. So for my first waveform, that is my 100 sine omega t. All right. So the 100 would be the amplitude. Yes. So we see that there. So 40 would have an amplitude of 40. Yes. Right. So based on our guesstimates, we can see that that is just less than 50. So yeah, 40. Yes. And for the periodic time, we know that we have 1, 2, 3. All right. So for the big waveform, if that was t, it means that this would be t over 3, t over 3, t over 3. All right. So these periodic times would be t over 3. All right. So that's what we were explaining earlier, if that is t. Okay. So I can now put in the other waveform, the 20 sine 5. So I have 5 waveforms within the same periodic time. And for my 7, I have 7 waveforms. Okay. Now, what I'm going to do is to add these waves. How do we go about adding the waves? Simply put, we just select any point in time. So we take an instant, yes, point in time, and we just draw a line. All right. And then we add the amplitudes along that line. So at this point, the 7 omega t looks like about 0. It's crossing the time axis. Yes. For the 5 omega t, The amplitude was 20. So let's say this is about, let's say 15. So that's 15. For the 40, that looks like about 35. And then for the 100, we'll have here maybe about 40, let's say 45. So the amplitude here would be 45 plus 35 plus 15 plus 0. So that would be 95.
Excuse me, sir.
Yes.
So what you're doing, you made a datum, you align.
I'm not hearing you clearly. I'm not hearing you clearly.
Are you hearing me?
I'm hearing you, but it's not clear. Go again. Go again.
Okay, so what you did, you put a datum here, which is selected a moment in time, draw a line, and you use whatever comes before it as the amplitude, and you estimate what height it would give or what amplitude it is.
Yes. Remember this, you would have had other lines. So I have only given you points of 0, 50, and 100. But let us say you were using a graph sheet, then you would have other
dimensions
in there. So you can find the actual value. So you wouldn't really have to be estimating. You'd find the actual value where the time, at that point in time. When you add them, in our case here, based on the estimates, simply because I don't have those smaller graduations, yeah? I have here it adding up to 95. So the sum along this point would be 95. So that is where my sum would be. And we'll do that along the time axis. We could come here. Yes, if I came there, then, and I'm estimating, this would be minus 40. This would be 100. Yes. This one would be, let's just take the 20. Yes. And this, let's say that's minus 20, that's minus 5. So we'd have minus 45 plus 120. Yes. Which would give us 75. Does that make it any clearer? All right, good. So that's how we're going to do the addition. But as I said, we'll go different points. Yep. And add accordingly. So let me remove that. All right. And so we first add the 100 sine omega and the 40 sine 3 omega t. And the green here, the graph in green, represents the sum of the two. All right. I can then add the third waveform, which would be the 5 omega t. Now let's look quickly at just the two. All right. And then we look at the 3. Now you will not see a major difference when I add the fourth. Yes, but yeah, there'll be some difference, I think, but not major. So I now add the fourth. Yes. Now let's go back to the 2. All right. Now, is there anything different between the 2 and the 3? Are you noticing any difference? Here's my 2. Here's my 3. Any difference?
Yes, sir.
There's an extra ripple.
There's an extra ripple where?
I'm going down, I believe, as in.
So you're seeing some extra ripples right there, right?
Yes, sir.
All right. So up here, you had just one incline and one decline, and then here you're getting some more ripples. As I said, however, when I add the fourth, it may not be very clear because of the small amplitude of the fourth. However, what you would not be able to determine just looking on is that this section actually goes up a little. All right. So, as I said, you really won't see it, but let us try and do a guesstimate here. That's about 75. Everybody will agree with that? So it comes down to 75, and the top section, let's say about 90. Somewhere there. I have no idea what it will be, but
it looks more like 80.
All right, 80. Not gonna argue. Okay, it's all I guess. Now for this one, all right, you can see, well, you may not be able to determine it, but this, let me clear that. That's messy. But this one, can't really see it, but I'm telling you, it's a little more than what it was before, because it still looks like 75. But you can also look at the middle section here, and this section looks a little flatter, all right? I agree with that? Looks a little flatter. So based on the trend that you're seeing here, what do you think will happen if I added another waveform, let's say sine 9 omega t, sine 11? What do you think is happening? Anybody? What do you think is happening? What do you think would happen?
Sir, the more waveforms they're going to become.
Go again? I didn't get the last part.
Yeah, the more waveforms there are, the flatter it's going to become.
And if it's getting flatter, what am I really creating?
Square wave or rectangle.
Absolutely. All right. So if this gets flatter, yes, then ultimately I'm gonna end up with something like that. And all right, the waveform that we'll produce will look like that. Okay. And what we just did is known as frequency synthesis. In other words, I know, and if you look at what we have here, if you look at the multipliers for omega, we have all odd numbers, eh? So we had 1, 3, 5, 7, and I just told you about 9, 11, etc. Now I know this, yes? However, you would not be able to just look at the square wave and say, hey, yeah, we need to add those odd numbers, all right? But let us say we knew the waveforms that we needed to add. Then adding them, we'll be synthesizing them. So we refer to that as frequency synthesis, yes? The reverse, however, is known as harmonic analysis. And harmonic analysis is what we actually do in electrical engineering, yes? Now, where have you applied this? Anybody want to hazard a guess? Where do you think you have applied something like this before? I'm telling you that you have already done it, you know. Where do you think you may have done something like this? Nobody? Come on, take a guess, you know.
Physics here.
Huh?
Superposition.
Superposition. No, you haven't done it with me, you know. I'm saying you have done it already.
No, in physics, there's something called superposition wave or something like that.
Oh, you mean that fancy thing? Ah, no. You mean instructive and destructive interference? That thing?
Fourier analysis.
Well, Fourier analysis is the process of getting the waveforms, but I'm telling you that you have already applied this. And you would have applied this principle when you were doing rectification. Yes? Now, it may not have jumped out at you, but you really have done it. And I believe everybody in this room have done rectification. Yes? But beyond rectification, what you had to do to get your waveform smoother, yes, was to create a filter. Yes? And the filter that you would have looked at your level would just be to put a capacitor in parallel. That's one option. Or you would have put an inductor in series. The question is, how do you determine the value of capacitance that you need? How do you determine the value of inductance that you need? Yeah. So the teacher, your physics teacher would have just told you to put, this size capacitor with so many microfarads, and you put it in, and when you look at the waveform, you see that it is closer to being direct current as against what the AC that you had before. All right. So that's one simple application of harmonic analysis. All right. And harmonic analysis is where instead of determining or knowing the waveforms that one needs to add, harmonic analysis determines what the component sine waves are. So we determine whether, we have all the sine waves or we have only odd numbered sine waves, or, yeah. So that's what the analysis is, yes. And that analysis is done using Fourier series, which is something that some of you may have already done in math, or you'll be doing it very soon. Okay? Alrighty. Now, if you note that 100 sine omega t, if we go back to the sketches that we had, yeah, what you will note, as we have already said, the waveform shown in black here will ultimately be a square wave. So the square wave would have been the complex wave. That's where we started this morning, saying that the square wave is a complex wave, yes? Similarly, the triangular wave. But here, we would have had our square wave, yes? So that's a square wave. And if you note, the 100 sine omega t, which is the wave here in orange, yes? We can talk about it. One, it has the largest amplitude. But also, note, it has the same frequency as the square wave. Or in other words, it has the same periodic time as the square wave. Yes? And that's the point we're making here. So that one major component has the largest amplitude, yes? And it has the same frequency as the periodic wave that we are analyzing. And we call this the fundamental. So the fundamental is that waveform which has the largest amplitude, and its frequency is the same as that of the complex wave that we are analyzing. Does anyone have any questions so far? Have I lost anybody? All right. So coming back to what we just spoke about, here's my wave that is going towards being a square wave. That's a wave in blue. And my fundamental would be your 100 sine omega t. Right? It has the same frequency as the square wave, or in other words, the periodic time is equal to that of the square wave. Of course, we know that frequency is equal to 1 over t. Now, the other components, these are also sine waves, but these sine waves have frequencies that are exact multiples of the fundamental frequency. Yes. So the 3 omega t would have a frequency which is 3 times that of the omega t. The 5 omega t would have a frequency which is 5 times that of the omega t, etc., etc. Yes? And these waves, we refer to them as harmonics. And we number, right? We number them according to the ratio of their frequency to that of the fundamental. In other words, the 3 omega t would be the 3rd harmonic. Yes? The 5 omega t would be the 5th, and of course the 7 omega t will be the 7th. Any questions? Any questions? All right. Now the Fourier series for a complex waveform is given by f of t, which is equal to a0 over 2, plus the sum from n equal 1 to infinity of a n cos 2 pi to n pi t over t, plus b n sine 2n pi t over t. And of course, these coefficients, the a n coefficient and the b n coefficient, and as well as a0 are found with these. Now, because I am fully aware that this is something that you will do in Fourier series, I am not, well, the syllabus asks for you to be able to just use the expressions, yes? So our purpose here is not for you to derive or to do the harmonic analysis, but to use the Fourier series to do your calculations. All right, so that's going to be how we will proceed. I will not ask you to do the harmonic analysis, because that is something that you will cover in mathematics. So you'll do both Fourier series and Laplace, which are just either side of the same number. All right, but I leave that to you and your math teacher. All right. So for your square wave, the Fourier series is given by that, and for your sawtooth, that's the expression. Okay, so what you'll note is that for the square wave, we have the odd harmonics. For the sawtooth, we have all the harmonics. So we have the odd and even harmonics. All right, and I'm not going to be asking you to remember these. You know, we will give you the Fourier series for these waveforms. And don't be bothered by the fact that we are alternating the minus and plus. All right, it will not impact the calculations that we will carry out with these Fourier series. Neither should you be thrown by the fact that in some instances you have a cos function. All right, so you get the sine or the cos, and of course we know that the cos function is just the sine function shifted by 90 degrees. All right. All right, so we have here 100 sine omega t. We have our 50, we have our 33. Note what I'm now doing. Yes. Here we have, right? And we have here the 2, 3. So I'm putting in the actual component. So we start with a half, then 1/3, then a quarter. All right. So that's a third. Okay. And what you'll find is that for the fundamental plus the second, this is what we would get. Yeah. If I then added the, so that's adding the maybe I should have shown this first before that. But anyway, so if I add the fundamental, which is the 100 sine omega t, and I have here the 50 sine 2 omega t, when I combine those, yes, then we'll get this. If I now added the 1/3, yes, this is now what I get. All right. And I trust you will see the progression that ultimately we are going to be getting something like that. All right. Which you can see represents a sawtooth waveform. So this would be straight down and then we go across. Okay. And as we add, we see that it is getting more pronounced. We are getting more ripples, which means that it is getting smoother. All right. And as I said, students, there is no requirement for you to, be remembering these formulae. Our purpose here is just for you to be able, or should I say, our purpose up to this point is for you to just appreciate the harmonic analysis and the harmonic synthesis. So you recognize that we are adding some sine waves, yes, and as we add them, we can create these complex waves, or as we have already called them, non-sinusoidal, all right? And we have to use these waveforms in electrical engineering for different purposes, all right? And we may be creating some of these complex waves. The complex wave I just mentioned, is of rectification. When you have your full wave rectifier, you would have gotten an output looking like that. Yes, that is a complex wave because it is non-sinusoidal. All right. If you were using a half wave, then you'll have that. That's a complex wave. So within this, what we are saying is that you're going to have some sine waves. Yeah. And those sine waves, which we say will have frequencies that are multiples of the fundamental, those are harmonics. And those harmonics would, we then determine which of those harmonics we want to filter out so that we'll get a nice smooth DC output. All right. All right. All right. Now, any questions? Because we're now going to delve into a little of the math. Any questions?
Not so far.
Okay. So when I said earlier that the work that we're going to be doing with complex waveforms really is the application or repeated application of what we did with AC circuits. Yes. So in AC circuits, we said that unless otherwise specified, we should always state the values that we give for the AC as the RMS value. And we know that it is the RMS value that we use to do our calculations. So we have to therefore know how to determine the RMS value of these complex waves. And that's what we're going to be looking at now. So for your RMS value calculations, we want to use a circuit supplied by 3 sources, right? And we want to determine the total power dissipated in the resistor. And the method that we are going to choose to use is the superposition principle. So I can find the power dissipated by R when E1 is acting alone, and then I find it when E2 is acting alone, and then when E3 is acting alone, and so forth and so on. All right. So if we apply that, all right, we know that P is equal to E squared over R. So overall, the total power we know would be E squared over R, where E squared in this instance would be the RMS of these combined. Now, why am I using these combined? Because each of these would represent, let's say, the fundamental and some harmonics. So they could have, based on the application that we're looking at here, we're saying that they have different frequencies. So each of them would impact the resistor differently. The fact that they have different frequencies doesn't matter, because the resistor does not respond to frequency, at least within the range that we're dealing with. All right, so the resistance remains the same with respect to frequency. Okay. So the power dissipated by each of the sources will be given by P1, P2, and P3, which is E1 squared over R, E2 squared, and E3 squared over R. And so we can now add these. All right, we can add these. So PT is equal to E1 or P1 plus P2 plus P3. And there's a point that I missed here that is important. E1, E2, and E3 represent the RMS values of each of the sources, yes? So we do our substitution and we get P to be equal to 1 over R times that. And of course, we know that P was equal to E squared over R. So we can remove the R from either side and we get E to be equal to the square root of E1 squared plus E2 squared plus E3 squared. All right. So the RMS for the overall waveform is given by the square root or the sum of the squares of the individual RMS values. The same is true for the current. Yes. Right, and you have this already in your notes, so you can just highlight what you need to highlight. For the current, the same is true. All right. Any questions? Any questions? All right. So again, you have this question in your notes. Just excuse me for a minute. All right. So we have a square wave, peak to peak, 5 volts. Symmetrical above and below ground. Calculate the amplitude of each harmonic up to the 7th. The RMS value of the wave. Everybody have this? Okay. Now you have an example there in your notes, but the first thing, you have it there for 2 volts. All right. So for this 5 volts, let's see now. So Morrison, Davey?
Yes, sir.
Okay. So what's the what will be the amplitude of this waveform?
$2.5, sir.
2.5. Okay. All right. And we want to find the amplitude of each harmonic. Now, what harmonics are there in a square wave? So Morrison, still with you, man. Which harmonics are present in a square wave?
Yeah, the odd one, sir. The one.
The odd ones, all right?
Yes, sir. Yes, sir. Yes, sir.
So our formula is for EM over pi times sine omega t plus sine 3 omega t over 3 sine 5 omega t 5 omega t over 5, etc. All right. So let's see, So Jones?
Yes, sir.
Which amplitudes would we be calculating?
We'll be calculating EM1, EM3, EM5, and EM7.
Okay. Mr.
Yes,
Beckford? Mr. Beckford?
Yes, sir.
Why would we not be calculating EM1?
Because it is the hit and the square wave are the same amplitude period. It basically.
Oh, yeah. But why are we not calculating EM1? Huh? What you just explained, what summarize that? What would EM1 represent?
The fundamental.
Exactly, that's all I'm asking. So EM1 would be associated with the fundamental. What did the question ask? Or you ask to calculate? Huh?
The harmonic component.
The harmonics. And how do we define harmonics?
The one that we make up
those that have frequencies that are multiples of the fundamental. All right? Okay, Mr. Jones, you understand why EM1 would not be calculated?
Yes, sir.
All right, so you would find the amplitudes for 3, 5, 7, etc. All right. For the RMS value, who is next in line? Ms. Hansen, for the RMS value.
You want me to calculate the RMS value?
No, just tell me what we'll be doing. I don't need the value because you have an example. I just want to ensure that people understand what they need to be doing.
You would divide the fundamental, the value that you get for the fundamental by √2.
I'm listening.
Yes, sir. You do it for basically all of them for 1, 3, 5, and 7, and then you find the sum of all of them.
The sum.
The sum of the square root
Oh.
of EM1, the sum of the square root of EM2, not 2, 357.
All right. Let's make sure we do it in the right order. You're finding the square root of the sum of the squares.
Yes, sir.
All right. So you're finding the square root of EM1 over root 2, all squared. I'm assuming this is what you're saying.
Yes, sir.
EM3 squared over root 2. Oh, EM3 over root 2 all squared plus etc. etc. All right. All right. Anybody unsure of what we should be doing here or what we're doing here?
Sir, what was the amplitude 2.5?
Amplitude, that 2.5 would be EM.
No, the reason why it's 2.5 because him said the peak to
Oh,
peak is
you're
5.
asking why?
Yes,
so
sir.
because
Oh,
peak
I'm
to
sorry.
peak-
Thank you, Ms. Hanson. Go ahead, answer.
Because the peak to peak is 5. That's from the top, the way the top to the bottom. So you divide it by 2. From 0 to the top, you'd get 2.5.
Oh, thanks.
Okay. And you note she said that because it's a square wave, so it's equal above and below. All right. Thank you. All right. Now this one is in your notes, but we are doing it because it's a little different from your regular. In this instance, what you have cos functions. So this one is in the notes. And here we ask you to calculate the DC component and the Rms values of the harmonic components up to the 6th. And we want the harmonic frequencies. Now, I'm telling you that the full wave rectified voltage, it has even harmonics. All right, so I'm telling you it has even harmonics. Okay, so if it has even harmonics, Mr. Henry.
Yes, sir.
If it has even harmonics, what would be the frequencies?
If it has even harmonics.
I'm telling you that it has even harmonics. So I'm asking you what would be the frequencies, the harmonic frequencies.
Not sure, sir. Not sure.
Skiles? So Skiles. All right, Richards.
Sure.
If you have even harmonics, what would be the frequencies of the harmonics?
Sorry, the frequencies will be multiples of 2 of the fundamental.
No, so tell me, we want it up to the 6. So what would be the frequencies of the harmonics?
So it will be cos 2 omega t.
No, that's the frequency I want. What would be the frequency of the harmonics?
So it will be 60, 120, 180, 240.
Okay. Now, I just said that we have even harmonics. So if they are even,
right,
would you get 60? Would you get 180? First of all, what do I mean by even harmonics?
Even meaning that they're multiples of 2 of the fundamental frequency.
Okay, so if given that, first of all, what's the fundamental frequency?
The same frequency as the rectified wave.
Which is?
Which would be 60.
Okay, so if we have even harmonics, what are the frequencies of the harmonics?
There will be multiples of 2 of.
Just give me the values.
Sir, I was giving them.
No, you were wrong. You gave me 60 and 180.
Oh.
What is 180 divided by what is 180 divided by 60?
3 times, sir.
Is that an even number?
No, sir.
Okay, so give me the harmonic frequencies.
So we would have 120, 240, 360.
Thank you, because you're asked for it up to the 6th. All right?
Yes, sir.
Good. So the third part of the question is already solved. All right. Now, how will we determine that we have a DC component? What do we know about a DC output?
It's smooth.
Meaning?
Meaning that
in the context of what we are discussing, how would we be able to identify which component is DC?
It's above the axis, the x-axis.
Yeah, but you would the Fourier series would not be able to tell you that. You won't be able to see that. What you just said, you know, we couldn't see. We're not seeing that. So what about the DC component? We could look at and say, yeah, man, that is the DC. You say it's smooth. The fact that it's smooth, what that mean?
Means that it's rectified.
Yeah, all right. Okay. All right. Anybody want to have a stab at that? How would I determine that something is DC? Remember, you know, I'm looking at an equation. How would I know that that component in the equation is representing DC?
Sir, when there is neither sine nor cos.
Thank you. There's no frequency. So the frequency is 0. Because, what was that? Freighter?
Yes, sir.
Because if you're going to have a cos function or a sine function, then you're going to have oscillations, no so?
Yes, sir.
Good. So once you see there's no cos or sine attached to the component, then you know it is the direct current component. All right. So if the expression, let's take this for me. The expression for your, but hold on, you have it in the notes, right? You know, yeah, this tells me
show
a lot.
us first, no, sir.
Huh?
And we can show us first, and we can tell you if we have it.
Yeah, man, but I know you have it. I'm looking at your notes. And what those two gentlemen are highlighting and what this class is highlighting is either you have not printed the notes, you haven't been reading the notes, which I suppose is why I'm getting the grades that I'm getting being reflected in the assessments. I told you up front, you know, students, and I don't beat around the bush. I suppose by now you realize I don't waste time. Right? I tell you as it is. Right? One of the things I hate is to teach anybody twice. In other words, I want people to succeed, but I know that the only way you're going to succeed is if you work. And you have to do the work. There is no way around it. You will have to do the work. Right? Absolutely no way around it. And if by some miracle you get through networks 1, you're going to buck up networks 2, and you're going to be in trouble. You know, and it is unfortunate, you know, because you have all of this material, and what are you doing with it? Anyway, we forge ahead. So we have a voltage V being equal to V1 M sine omega t, 2M sine 2 omega t. Of course, the 2M and 3M, etc., are just the amplitudes of the individual components, right? And if we connect it across a resistor, remember now, when we're looking at AC circuits, one thing we know is that the current and the voltage across a resistor, across and through a resistor, are in phase. We know that, okay? So in other words, you will not have any phase displacement shown in the current expression. So the voltage and the current will be in phase. That is if, of course, I'm connected across a purely resistive circuit. If, however, I was to connect the same supply across an inductive circuit, then of course we know that the current lags the voltage by 90 degrees. Now, let me quickly point out that in complex wave, or for this topic, we do not use degrees, we use radians. So the angles are all in radians. So of course, you know, you're in an exam. For your regular AC circuits, you know that we use degrees. However, once we switch to complex waves, although we are still doing basic AC circuit theory, put a calculator in radians. Please, please, please. All right. So the current expression when across an inductor, as I said, we know that the current will lag by 90 degrees or pi over 2 radians. And so that's where we get the minus pi over 2, because the minus there is telling us that it's lagging. And of course, the pi over 2 is telling us by what angle. For your capacitive circuit, so if it's purely capacitive, then we'll have pi over 2. So the phase angle by which the current components will lag will all be dependent on the type of component that we are connected across. Yes? So if I have a combination of elements, whether I have a combination of inductor and resistor, capacitor and resistor, or all three, I will have to find the individual phase angles. With an inductor, I know it's 90 degrees or pi over 2. With a capacitor, again, I know it's 90 degrees or pi over 2. With a resistor, I know it is 0. But once I start combining them, then I know that it's going to be something. Right? And we have here phi. Right? Also, not only is it phi, but we don't know whether or not it is going to be negative or positive. Well, this one is left out. So it's plus or minus phi. Yeah. Where of course phi 1, phi 2, and phi 3 are dependent on the components. I1, of course, and note these are amplitudes that we are dealing with. I1 would be V1 over Z1, I2, V2 over Z2, and I3, V3 over Z3. All right. So let's just see how we apply all of this. All right, take this question for me. All right, are we finished with this?
Just a moment, sir. All right, sir.
Okay. All right. So let's see how we would approach something like this. First of all, it's connected across a resistor. So if the circuit is connected across a resistor, the first thing we need to do, of course, is to draw a circuit. So we have, oh, come on, Zach. All right, so we have our resistor, and we have our complex wave. Okay, so that was 10 ohms. All right, so we have 120, 20, 15. So V is equal to 120 sine omega t, 20 sine 3 omega t, and 15 sine 5 omega t. All right. Okay. So we want an expression for the current. Now, our current, and please note students, each time I write the current or voltage expression, I want to go back to our page. Note, I use lowercase because what this represents would be the instantaneous current and the instantaneous voltage. Okay? So these will be the voltage and current at a point, at a time t. All right, just bear that in mind. However, when I'm writing the voltages, the component voltages, I use uppercase as well as uppercase for the current. Just bear those in mind. All right, so back to the question. So now, how would they, for the fundamental, and the approach here is that we're going to take each component, so each of these three components, we're going to take them and see how the resistor would respond to each. That is how we are going to approach it. Or in other words, we are going to be applying the superposition principle. All right, looking at how each component behaves and then add them. Are we clear? So for the fundamental, how would it impact the resistance? How would the frequency of the fundamental impact the resistance? All right, I suppose I should just leave this for you to work on your own, right?
Excuse me, sir.
Yeah, man.
Can you hear me, sir?
Yeah, man.
Okay.
Loud and clear.
So the frequency, since it's purely resistive, sir, it wouldn't affect the resistance.
Okay. Fair enough.
Frequency does not affect the resistance.
So for the fundamental, what's the current, the corresponding current?
What's the current?
Yeah, the corresponding current for the fundamental.
Well, it would be 120 divided by 10.
Okay, which is?
Which is 12. So the angle would be 0 sine omega t. Yeah.
All right. So there's no phase shift, so we just have 12 sine omega t. All right, for the third harmonic?
The same 120 divided by, 20 divided by 10, which will be give you 2 sine 3 omega t. And continue.
Okay, and then 1.5 sine 5. All right. You're asked, okay, so you just want the expression for the current, okay? All right, so that would be the current expression. Next, we have a 9 point, did I give? Okay, I didn't. All right. Next, we have the inductor. And it's 9.55 millihenries. Okay. So what do we first need to do?
Find the inductive reactance.
Which is? Which is?
2 pi FL.
Okay. F here is 50. So calculate that for me, please. It was left out of the question, but take it to be 50.
3 ohms, sir.
Huh?
3 ohms.
3 ohms. So for the fundamental, just remember you need to take each component. So for the fundamental, XL is equal to 3. Okay? So what would the corresponding current be equal to? If XL is 3, what's the current?
Would be 40 sine omega t.
All right, so it will be 120
divided
over
by
3 sine
omega t.
What?
3 omega.
No, the voltage is 120 sine omega t. What are we dividing by here? What does that 3 represent?
The reactive
inductance.
The inductive reactance.
Inductance.
The inductive reactance. So if it's the inductive reactance.
Current overlap by 90.
So how do I write that?
So it's sine omega t minus pi over 2.
Thank you. All right. So that gives me 40 sine omega t minus pi over 2. All right. For the third harmonic. For the third harmonic, that is XL. Let's work that out for me. What is XL equal to? What do we mean by third harmonic?
6, sir. XL equals 6.
What do we mean by third harmonic?
3 times as 3 times the wave moving 3 times fast. You have three times more waves as a fundamental.
So what that mean? What that mean?
The third harmonic will be 9. That's 9.
What does it mean? You say you have three waves. So what's the implication? You have 3 waves fitted in the same periodic time as the fundamental. So what does that mean for that wave?
The frequency is higher, sir.
Pardon?
The frequency is greater.
You have 3 waves fitted in the same period as the fundamental. So what does it mean?
Frequency is 3 times the fundamental.
Thank you. It is 3 times. I don't want to hear anything like it is greater. I don't want to hear anything like it is less. Gentlemen and ladies, you're in engineering. There are a couple of things I have not said to you before, but listen to me, folks. You see, in this line of business, we hold people's lives in our hands. Did you know that? Did you understand that? When electrical engineers, when engineers make mistakes, when engineers are not sure of themselves, they kill people. I can't say it any more blunt. When a doctor makes a mistake, he kills the sole patient on his table. When we make mistakes, we run the possibility of killing hundreds. So I don't want, if you are going to believe that you're gonna go through engineering with this shy, bashful thing, go take up sewing. But if you're going to continue with this area of study, yes, I tell you, this is the time you put yourself out there. Don't be afraid to get it wrong. What's wrong with you people? Put yourself out there. I have absolutely nothing against people getting stuff wrong right here during the lecture. This is when you get it wrong, because this is where I will help you to understand why you get it wrong. Make the mistakes now while we are online, while we're in class. So the third harmonic means that the frequency is 3 times as great. So what would be the frequency that we're dealing with here?
150.
150. So calculate 2 pi f for me and you get what?
9.
9. So what would be the current component at this point? I should put that as IM1, IM3. What's the component here?
120 divided by 9.
No,
times.
120 was the fundamental. So what's the third harmonic?
Oh, 20.
20. So we have 20 over 9 sine 3 omega t. And what's the angle?
Minus pi over 2.
Minus pi over 2. All right. Whatever 20 over 9 is, we don't really need to worry too much about that. All right. So we now go to the fifth harmonic. So for the fifth, what is XL equal to?
15.
First of all, what is F?
250 hertz.
250. So XL is equal to?
15 ohms.
15 ohms. So I5M I5M equal
15 over 15. Sine 5 omega t minus pi over 2.
Thank you. All right. So now what you were asked for was the current expression. So I can now write the current expression. So we now put all of them together. For the fundamental, it was 40 sine omega t minus pi over 2. For the third harmonic, it was 20 over 9 sine 3 omega t minus pi over 2 plus 1. And I'm just putting in the 1 here, but obviously you don't need to. 5 omega t minus pi over 2. Does anyone have any questions?
Sir, how you get the 15 for the fifth? For the oh
Okay. Any other question before we go to part 3? Whoops. Oh Lord. I discarded the, anyway. All right. So we have 40. Anyway, let's just go to the third, the third part of the question. I discarded the first sections. Anyway, we're asked to, for you have a 10 ohm and you have the inductor. So this is now our circuit. Okay, my square wave is here. This is 10. This is 9.55 millihenries. Now, a couple of things you need to note. The first one is that when you were calculating XL just now, right? You were going, I asked you to look back at the frequency. So you found for the third harmonic, you know, that was 150. For the fifth, it was 250, etc., etc. Okay? Now, you would note, however, that if the fundamental was 3, because you are dealing with inductive reactance, and we have here 2 pi FL, then for the third, it will just be 3 times 3, which would be 9. For the fifth, it will be 5 times 3, which will be 15. If I want the 10th harmonic, then it will be 10 times 3, which would be 30, and so on. So you don't really have to go back and recalculate if you bear this in mind. Of course, the reverse will be true if you're dealing with a capacitor. All right? If you had a capacitor and the fundamental was, say, 20, yes, 20 ohms, then for the third harmonic, it will be 20 over 3 because it is 1 over 2 pi FC. All right, so you'd have an inverse relationship. All right. But if you're not comfortable with that, please use your fundamental, go back to your frequency and recalculate. All right, it will come with time and practice. Okay, so in this instance, what would
Excuse me, sir. Are you doing part C of the question?
Yes, part C.
Part C states R is 15 ohm and L is 19.1.
19.1.
Right.
Okay, 19.
And I see where R is 15. I think it says 15.
Oh, 15 and 19.1. Thank you. Thank you, Mr. Morrison. Okay. Obviously, 19.1 is just 2 times 9.55. So it means that the inductive reactance would be 6. All right. So now we want to, again, look at each component. So we start with the fundamental. So we say for the fundamental, okay, you're going to have to apply superposition, right? So for the fundamental, XL is equal to 2 pi FL, which is 6 ohms. Everybody calculate that?
Yes, sir.
R is 15. So it means that Z is equal to the square root of 15 squared plus 6 squared. whatever that is equal to. So what is Z? And by the way, this is the modulus of Z.
16.2.
All right. I paused because I just wanted to double check. This is 16.1155. All right. You're doing these things, you don't round off so quickly, all right? You do your rounding off at the end, Miss Hanson, all right?
Yes, sir.
Good. All right. But I leave it for now. What is phi?
Sure would be.
What's phi? Theater.
I think it would be 21 times pi over 180, which is equal to 0.3.
Go again?
21 times pi over 180.
What is phi?
Which is 0.36.
0.3666. What's the unit?
Radian.
Okay, so it means that I1, yes, would be 120 over 16.1. What's that? All right, I give you 16.16. All right. Sine omega t. Would this be plus or minus?
Minus, sir.
Why minus?
Oh, minus.
Because it's logging the voltage.
Because it's inductive.
The current, yeah, it's inductive.
So 0.36. All right. So that's for your fundamental. You then go to your third harmonic. So for the third harmonic, yes, what is XL? Come on, man, we just talked about this, you know. What would XL be equal to?
18.
18. And what would R be equal to?
15.
So just give me this values for Z and phi.
So that is 23.43.
23.43. And phi? Phi?
0.876.
0.876. So it means therefore that for I2 will be equal to 20 over 23.43. And we have sine 3 omega t minus 0.876. Is that what it said? Yeah. So go ahead for me and find
Sir.
For the fifth. Yes?
Sir. I didn't quite get how did we calculate the phi, sir? Please.
Same way we did it with AC circuits. All right? Inverse tan of XL over R.
Okay.
No problem. For the fifth?
Z is 33.54.
First of all, give me XL.
Oh, sorry. XL is 30.
And R is 15. So Z, you said it's 33.54. And phi?
1.107.
1.107. So it means that I3 will be 15 over 33.54 sine 5 omega minus 1.107.
So should that be I5 instead of I3?
And it's supposed to be 3. All right, now folks, the question didn't ask for it, but I wanted to calculate the RMS current. So if we wanted the RMS current, okay, anybody?
Sure, would it be the
This is for part 3.
Or divided by root 2?
Go again. So we have the square root.
Would it be the I1 squared plus I3 squared
All right.
plus I5 squared?
So that's the. All right. So in this case, based on what we just wrote, it would be I1 over root 2 all squared plus I2 I3 rather, over root 2 all squared plus I5 over root 2 all squared. You can make the substitution. However, what is the square root of 2 all squared?
2, sir.
2, sir.
2. So I could rewrite this as I1 squared over 2 plus I3 squared over 2 plus I5 squared over 2, which is the same as I1, I2, I3, I don't know why I keep insisting on writing 2, I5, all squared over 2. All right? So instead of having to individually divide the components by root 2 and then square, you could simply square each component, add them, divide by 2, and then find the square root. So you can do that on your own time and just test the legitimacy of what we're saying. Okay, folks, well, if you have no questions, that's it for today. If you have questions, ask now.
Sir, can speak to you after this session.
Mr. Henry, you're the person who penned something to the union, etc., and the head of school?
Yes, sir.
Yeah, man. Continue dealing with them on that. All right. That's it for me for today. All right, students. Have a good afternoon.
Yes, sir.
Yeah, cool.